Yeah, the rest I think might be kind of hard. But so I'll just bring it up though. It could be like a challenge problem. So this one, I'll actually admit, I worked on this very briefly, so I have a couple of ideas, but maybe you guys can help me finish it. So this is from the same Olympiad as the very last video I did. So this Christmas special mock geometry Olympiad. So we have a triangle ABC. For the actual competition, like you could take, basically I think all the problems are like due on February 2nd or something, and you weren't allowed to use GeoGebra, but you could do it, you could spend as many hours as you want, I think, on it. If that's not right, you guys can correct me, but I think you could spend as long as you wanted to do the problems, as long as you submitted it by February 2nd. We have a triangle ABC, I is the end center. The circle with diameter AI. So this reminded me a lot of like the Sharky devil configuration. So I'll explain that later. Probably some of you guys have seen my video on the Sharky devil configuration, right? That was a really complicated one.
I haven't seen it.
Maybe I'll bring it up here as I work through this. So the circle with diameter AI, it also passes through E and F, right? Because AFIE is cyclic. And it intersects omega at S. M is the midpoint of arc BAC. This is M. MI intersects the circle at T. Oops. The circumcircle of MIS. It's a lot of circles. So actually, before I even draw the circumcircle of MIS, these two circles are tangent because basically by the in-center x-center lemma. So I actually mentioned this in one of my previous videos, but basically you have the circle with diameter AI, right? And then by what we were talking about, G is like the midpoint of arc BC. It's the circumcenter of triangle BIC, right? So from there, it's not hard to see that these two circles have to be tangent, right? So then we draw the circumcircle of MIS, and it intersects that circle, the circumcircle BIC at the point X. Wow, there's a lot of information. But I'll bet we probably don't even need all of it. The tangent at S to the big circle intersects BC at point V. And we want to show MX and VT intersect on omega. So if I draw VT and I draw MX, they do indeed intersect on the circle. So I worked on this problem just a small amount of time, so I'll admit that. But I noticed that AD also passes through that point, and I feel like that has to help in solving this problem. So I was thinking maybe I could let AD meet the circle at a point, and then I could show BT and H are collinear and MX and H are collinear. Maybe that would work. Just check who's still here. So can we show VT and H are collinear and MX and H are collinear? Let's see, if we show MX, trying to think. So I wonder if we can like use the radical axis theorem to show that TH, BC, and VS are collinear. I wonder if, let me think.
This sounds difficult.
It does feel hard. Let's see. I feel like at least I feel like I might be able to show VT and H are collinear. There's got to be like a trick using the radical axis theorem. I wonder if, no, VI I don't think is tangent to the circles.
Michael, the lines MX and ID intersect at the circumcircle of BIC. Does it help on something?
Oh, they intersect on the circle, is what you're saying. It's like
On
cut off. Yeah, no, I see what you're saying.
Yeah.
I think it probably might help. So ID and MX intersect on the circle. Maybe that would help us show that MX passes through H. How did you find that? How did you find that ID and MX meet on the circle? Do you remember how you got that?
What?
Do you remember how you proved that ID and MX meet on the circle?
Oh, ID?
Yeah. You mentioned that ID and MX meet on this circle.
Oh, I actually didn't prove it. I
Ah.
just told you. I just saw it. I draw in GeoGebra online.
Nice. All right, let's see. Yeah, so yeah, it's kind of like that feels like it should be provable that they meet on the circle. Let's see. So if I let ID meet the circle at a point J, and then I want to show M, H, and J are collinear. That feels like it should be provable. So let's see. But yeah, if we could show that, so yeah, it's like M, X, H, and J all lie on a line, right? It's pretty interesting. Let me see. Let me still keep thinking about my radical axis idea to show TH passed through V.
This sounds pretty difficult.
I'm not
Pretty
gonna.
difficult.
I'm just gonna try for a couple minutes. Yeah, it does seem difficult. That's definitely true. So, what is the radical axis of? Have you seen anything on like point circles? So, like a circle with radius 0.
Yeah. I tried to solve one problem yesterday.
Like that. So what if we have the point circle S, and then we have the circumcircle of ABC, and then we have this other circle for DI and C, and we try to use the radical axis theorem. So basically the radical axis of the point circle S and the circumcircle of ABC, that's SV, it's the tangent line at S. And then BC is this other radical axis. But what is the radical axis of the point circle S? I don't think this would help as much, but let's see. Oops. Yeah, no, I don't think that's what I wanted. Oops. Let's see. We have T and H. Like we want another circle that goes through T and H. What about THD? I think the circumcircle of THD might be tangent at D. Yeah, it looks like the circumcircle of TDH is tangent at B to the line BC. Maybe that might help. So this V, yeah, if we can show that, then that would show that PH and V are collinear. So can we show the circumcircle of TDH is tangent to BC? I might just assume that for now, because then that would mean the three radical axes would be
that means that the center of the circles are collinear with point D. Like we should just prove that
this
segment. Let me try to explain better. Like,
no, I see what you're saying. You want to show that the centers of the circles are collinear with D. And
I'm sorry, I got off because my internet connection wasn't very good.
it's all right. No worries. But basically, I mean, once we do show that, we can then use stuff with the radical axis theorem to show that TH and V are collinear. And then, I'm sorry, did you ask how? Oh, Arabian math, what did you just say? I'm sorry.
Yeah, we can extend that line TD to intersect the circumcircle of triangle ABC at a point A dashed.
We can extend TD at a point A dash,
yeah,
is what you're saying.
to meet that line. Yeah, then we can prove that the A dash is parallel to the line BC.
Okay. So let's see, how do we show?
Yeah, then we can finish up the reams.
Oh, because since THBC is cyclic, then I think I see it. So how do we show A prime is parallel to BC? Is that obvious that A prime is parallel to BC?
A what?
Yeah, it's a well back. I've seen.
What?
Yeah, actually, this line TM and line TD are isogonal with respect to angle BTC.
Line TM and TA prime are isogonal with respect to BTC. Let's see. Well, so TA and TA prime are orthogonal with respect to BTC, right?
I don't understand why.
Let me see. I'm seeing so many things all at once. T is also the point of tangency of the mixed linear interval. This configuration is just crazy. So, you know how I was just talking? Oh wait, hold on a sec. Oh, T, yeah, it's just. I'm seeing so many things here. It's crazy, but yeah,
Because there's too much information.
yeah,
Like,
so yeah, like there's also that mixed linear in circle. This lemma was an EGMO. I'm sorry, I don't have EGMO right. I don't have EGMO with me right now, but could you sort of describe the proof that's an EGMO? Or we could look it up, because I know there's other webs, like, we don't have to look it up in EGMO, the book, but Evan Chen also has a handout on the internet that's free, where I think it has that fact that A prime is parallel to BC.
but how did you define A prime?
A prime is the intersection of TD with the circle.
Again, this sounds pretty difficult.
But I think we're actually really close to solving it, because as complicated as it is, like,
But if we prove that A prime is parallel to BC, we prove it?
we proved the first part of it. So if we prove A prime is parallel to BC, then that proves that PDH is tangent at D. And then that could be used to prove that VT and H are collinear.
But then, like, VT and H would be collinear because of what?
So we could basically, so by the radical axis theorem, but basically I could show V has the same power with respect to all three circles, because, so I'll type it out, but, so we'd have VD squared is equal to VS squared is equal to VB times VC. So if we knew it was tangent, we'd have VD squared as VS squared.
Oh, I got it. Nice. So I'll just erase my whole figure here, like my whole drawing, and I'll just try to prove that A prime is parallel to BC. But why does proving that A prime is parallel to BC we finish the problem? Why is it?
Or why does showing A, so it doesn't solve the whole problem, but why does showing that A prime is parallel to BC prove that PDH is tangent?
Yeah, why does it like show that it's tangent?
Yeah, so basically that would mean that angle PHA is equal to angle TA prime A, which is equal to angle TDB. So we would have
Oh, I think I got it. If you wouldn't have BC tangent to both circles.
yeah,
Nice.
TDB. So basically we would have this equality. So if angle THA is equal to angle TDB, then that means it's tangent at D.
Very nice.
And so then by this, actually, I don't even know if I wrote it right. So So Vs squared is Vb times Vc, which actually now I'm trying to remember what I did here. And then Vb squared. Yeah, actually, what did I just do?
Point H is the intersection between MX and the circumcircle, isn't it?
If we can prove that, that would solve the problem. If we can show that MX and H are collinear, that would solve the problem. And in fact, you were saying that MX, H, and J are collinear. So I'm not sure how to prove either of those. But yeah, if we can show MX and H are collinear, that solves it.
Really nice and difficult problem.
Yeah. Let's see. So is it obvious that VD is equal to VS? I'm just trying to think. Feels like it should be obvious. We can make use of the fact that.
Michael, can you read the chat?
Yeah. So hold on one second. So Arabian Math said maybe we can use that S, D, and G are collinear. Actually, I saw this before, but I forgot about it. But so yeah, there's just so much stuff in this figure. So S, D, and G are collinear. I think we can use some stuff about spiral similarities to prove that. I think
I don't know spiral similarity.
but yeah, maybe I could teach it to you here. It's actually really just similar, a fancy way of saying similar triangles. Don't worry, I'm learning also with you. So the S, D, and G. Let me see if I can explain why they're collinear. So I'm just trying to think through how we would prove that. We want to show angle ASG is equal to angle ASD.
Like G? No, G is not the midpoint. No, yeah, G is the midpoint of the arc BC. And
Yeah.
we could try to use that SBG should be equal to GSC. Maybe we could try to explain.
BSG is equal to CSG. And so if we can show SD is the angle and it's an angle bisector, that would solve it. And I think we might be able to use projective geometry to show that, which I know you said you haven't learned it yet. But let me just think for a second. And actually, I think all this stuff I may have already proven in another video. I just don't remember all of it.
But maybe we could try to use the ratio like between BD and DC. And like there's a very similar construction with the orthocenter of the triangle, like very similar. That wasn't a problem here from Brazil, that we should prove that these two lines intersected at a point. But I don't know if it's like just for the orthic triangle or it can be for any triangle. I don't know these names in English, but
it's okay. But so you think there's like another theorem like related to the orthocenter that you could use to prove it?
wait a little bit. Let me just.
So yeah, using projective geometry, I think it's not that hard to show that FV is the angle bisector of VSC. So I'm just gonna write it out quickly here. Let me see for a sec. Yeah, it's obvious using, so yeah, I'm just going to write this out for the viewers. So we have angle MSG is 90. That's clear since mg is the diameter. And so also,
Michael, I think my guess was correct. Like for any I don't know, like if you get any point inside the triangle ABC, the perpendicular to the sides, if you take this point and draw perpendicular to the three sides, and that will form three cyclic quadrilaterals.
Oh, Michel's theorem, right? Yeah.
Kind of Michel's theorem. It's like you can form cyclic yeah, you can draw it. It's better to explain. I'm not professional in English yet.
All right, you're pretty good.
Yeah, and if you take the circumcircle of N or QW,
all right,
and take the circumcircle of ONP, they intersect in a point, and the bisectors intersect at the circle.
Hold on just a sec.
The bisectors of the angles OZP and ONP intersect in the circle.
Well, we know that the angle bisectors are always going to intersect at the midpoint of that arc, right? So but it passes through.
So we just need to prove that. We need to prove that it's the bisector. Yeah.
Exactly. So yeah, we need to show SD is the angle bisector of BSC, and that I claim using projective geometry is quite easy. So But yeah, it's basically like, so yeah, I'll just give you a flavor of it just because you haven't seen too much projective geometry before. SFE is similar to SBC. Yes, I think that's true from properties of spiral similarities that SFE is going to be similar to SBC. There's a lot of stuff going on here. In fact, I think there's so much we can say about this configuration. It's absurd, but in fact, FO over OE is equal to BD over DC. That's,
Oh, yeah.
yeah, no, I know how to prove SD and G are collinear. I'm just trying to show, I'm just wondering, how do we show M, X, and H are collinear? SF over SE is equal to BD over DC. I know how to prove that fact, Arabian math. So yeah, I know that do you see how to use all this stuff to show that M, X, and H are collinear?
I truly don't know.
But yeah, I'm wondering Arabian math. Do you have an idea if any of this stuff can be used to show that M, X, and H are collinear?
Yeah, I was thinking of using the Reims theorem, which says that if we extend that line MX and yeah, we can go by the phantom point approach. We can for now we can just assume that MX intersects the circumcircle of triangle ABC at a point H dashed.
Okay, and then so if MX intersected it at a point H prime, let's say. Oh, whoops. Yeah, I don't want to make it look like it. And yeah, we don't know yet that it intersects at this point. But did you have an idea? So you're using like a phantom point approach, right?
Yeah. Now, SI intersects the circumcircle of triangle ABC at the antipode of A.
Or what intersects it at the antipode of A?
The line SI.
The line. So you're saying this is this point is the antipode of A? Is that right? Oh, SI, yes, SI intersects it at the antipode of A. I'm going to write this all up. Okay.
Yeah, by the Reims theorem, we can prove that MX is parallel to line PQ.
MX is parallel to P, or MS is, or what did you say is parallel to PQ?
Line MS and line PQ.
MS isn't parallel. MS isn't necessarily parallel to PQ. They intersect at a point. So yeah, just a heads up to everyone, I'm going to stop in about a half hour. Usually I try to make it like 3 hours. Okay.
Oh, okay.
Yeah, I don't want to take up your whole day. I know this is super fun, but yeah.
Yeah. So, what are the other problems do we have here?
You want to take a look at some of the others?
Some other problem? Yeah, because I think I won't be able to solve this one. Like,
Okay. The others were, yeah, this one was kind of hard. And it also used a lot. I think I haven't solved it yet, but it uses, it's almost like a similar configuration of that one. But let's see, maybe I could come up with another problem. Do you have a certain country, or do you have a certain test that you'd like to look at?
I don't know, like Brazil test.
Let's see, let's check it out. So Brazil, I know they had the Brazilian Olympic Revenge. Here it is, Brazil.
No, Olympic revenge is so difficult.
Olympic.
So difficult. It's like for the university guys, the teachers.
Oh yeah, I had one of their problems on one of the sessions on my channel, and yeah, we couldn't solve it. It was just so hard.
Stupidly hard.
Yeah, but here's.
It's just level 2 there.
I think, let's see, level 2, level 3.
Level 3, yeah. There's a problem. Very nice. I've never tried it, but it looks like a lot. It's 2017.
All right, let's check it out.
It looks like this one. Yeah, problem 5, P5.
Okay.
It looks like a lot the other one you put there. I don't know why.
Interesting. You want me to try it?
I don't know. I want to try it.
Okay.
I don't know if I'll get it, but because I'm still on level 2, like, but I'll try to do it.
It's all right. Is there another problem you want me to solve for the last half hour?
You could try. Yeah, I think you could solve it. I don't know if I could, but yeah. It seems to be a very nice problem.
All right, let's check it out. I think I have a blank one here. All right, let's check it out. Whoops. Yeah, it's so weird. Sometimes it doesn't work the first time. That's weird. Okay, I'm not gonna just check the whole thing out. So we have a triangle ABC, and RA passes through the midpoint of BC, and it's perpendicular to the internal bisector of angle BAC. Okay.
Yeah, like this.
And then we draw the other lines. Okay.
Mm-hmm.
So we have that, and then we have this. And they form a triangle, and we want to show the circumcenter of it is the midpoint of HI. All right.
It seems beautiful. I don't know, but
it looks interesting. Let's see. So we have this, and I think it's
let me just see. Or A is the perpendicular from C.
So it's, I could try to highlight the 3 lines. This line, this line, this line, and this line. Oh no, actually it should be F should be this point instead. Yeah, so I'll draw that triangle and I'll hide the rest. Let me draw the angle bisectors. B to I, C to H.
It's very confusing.
Yeah, it's tricky. And I'll draw this point. Okay. Let's see how that looks. Let me make it full screen too. That would probably help.
We want to prove that the orthocenter of the new triangle is the midpoint of HI.
Oh, wait a sec. I have a feeling I didn't, because I didn't even draw the midpoints of these other 2 sides. So something I did can't be right. Yeah, no, I didn't. I just drew a perpendicular from
C, yeah.
Yeah, that's not right. All right. I think that would probably even make the diagram easier because I could. Yeah, let's see. Okay, so I need the other midpoint. That's a midpoint. That's a midpoint. Let's see. Yeah, I want to make the midpoints not so close to the. And then that perpendicular.
No, that's right.
Yeah. Okay. Let me move it up a little bit. So I'm just going to highlight the 3 lines we want. So this, this, and this. Okay.
I think so, yeah.
So that, and that. And might have already drawn AJ. Yeah, I want to draw these points, like this point. Oops. I'm going to hide some stuff, but just make things nicer. All right, let's start hiding stuff. Let's see. Maybe that's it. I think that should do it. Okay, so this is an in-center, I, and then I'm going to draw, let's change this from H to something else. Call K, let's call this M. So there's actually a trick to doing the orthocenter. So I could just do this, triangle center. I think it's ABC4. So the orthocenter is way in the corner right there.
Oh my gosh, what a, oh my gosh. What a tricky drawing, yeah.
Yeah, it's very tricky. So we want to show the mid, let me check. If I draw the midpoint of HI, it's the circumcenter. It is. All right.
Yeah, fortunately. Yeah.
Okay, let's see if we can prove it.
Oh gosh.
So there's a theorem. If we draw the 3 feet of the altitude, so I'm going to draw the end circle. Let me see. Okay. And then we can also draw the 9. So you know about the 9-point circle?
Yeah.
So that's the circle through D, E, and F, right?
Yeah. It is tangent to the encircle, isn't it?
Yeah, by Feuerbach's theorem, it's tangent.
Yeah. I don't know how to prove it, but I just know the fact.
It's I saw there's not. I might do a video on my channel, but yeah, it's not that simple of a proof. So I kind of like this diagram for now. I wonder if H and I are isogonal. Do you know about isogonal conjugates?
Yeah.
Let me check if H and I are isogonal conjugates in the triangle GMK. So that's 30.8. Yeah, no, I don't think so.
Sounds pretty difficult.
Yes, but let's see. Let's not give up just yet. Is I the in-center of GMK? I don't think it is. Maybe it is.
Oh gosh.
No, I is not the
No.
in-center. But what's really interesting is like this angle bisector. It looks like it. Let me check if there's like a concurrence here. No, I don't think so.
Yeah.
Let's see. So basically J. Like IJ is perpendicular to MK, and then let me call this P. IP is perpendicular. So basically, if you look at the triangle GMK, P, J, and L are the 3 feet of the perpendiculars from I, right?
Right. Yep.
And there's like a lot of theorems about, like whenever you have a 3 perpendiculars like that, there's like a lot of theorems that relate to it.
There are some cyclic quadrilaterals there too.
Yeah, like IJKP is cyclic, and so on.
Isn't I another point from triangle MGK?
I'm wondering, is it it's not the in-center, but maybe it's something else. Yeah, it's not the in-center.
Isn't it the orthocenter?
I don't think so, because like if you drop a perpendicular from M to GK, it doesn't pass through I.
It's not the circumcenter too, and it's not the centroid.
Yeah, but maybe maybe we can still say something about it. So we want to show the midpoint of HI is the same distance from M, K, and N, right? Let me draw the 9-point center. So so that's the 9-point center. The 9-point center, it's the midpoint between H and the circumcenter. Yeah, let's do this too. I'm going to draw the circumcenter of ABC. What R? So basically RD, RE, and RF are all perpendicular because R is the circumcenter. And not only that, Q is the midpoint of HR, and N is the midpoint of HI. So Q
and Q is parallel to
IR, yes.
What is OR?
I'm sorry, what did you say?
How did you define OR?
R is the circumcenter of ABC. So I didn't draw the circumcircle, but it's the circumcenter of triangle ABC.
Nice. Okay.
All right.
So it's parallel to line OI. Yeah.
So basically, if Q, I forgot what Q was. I think Q is the center of
Do you know Rodrigo, who's with us today? Like, who was with us today from Brazil?
Yeah, Rodrigo Porto. I saw he was on.
Yeah.
So he was on. I'm not sure if I'm trying to remember if anyone else from Brazil has been on. I'm not sure. Other than Rodrigo, I'm not sure.
He said, he told me yesterday that he had solved this problem, and for this he gave me a hint.
Okay.
Can I read it?
Yeah, sure.
It's like he said to look at the omodity center that takes this new triangle GMK to the triangle made by the X incenters. Like,
oh boy, X centers.
Yeah, he told me this, and I was like, what?
It looks familiar, like oh, whoops, sorry. So we want to show N is the circumcenter. Basically we'd have NH is equal to NI and NM is equal to NK, right?
We have this,
Or-
NM equals NK.
Oh no, I'm saying if we wanted to, if we proved it, but no, I haven't
Oh,
done that.
makes sense.
Yeah. Let's see. Arabian Math has a similar problem. I'll check it out in the chat.
He said that I have requested a top secret page for which I have not received security clearance.
Oh, in the link, in the Zoom link?
No. On the link he sent me from AOPS. He said I can access it. I don't know why.
Oh yeah, it's a certain geometry marathon. I think, yeah. We'll try to get you access. All right, thanks Arabian Math. But yeah, I'll type the lemma. I'll just type the lemma in Zoom. But I'm assuming you mean P7, Arabian Math. Sorry about that.
It sounds pretty difficult.
So I just typed the lemma he was mentioning in the chat. But yeah, let's work on it for a couple more minutes. But yeah, then maybe we'll just finish it off.
Let me just see it. Here. It's trying to solve my AOPS name.
All right. I like it. Okay, so let's see what Rodrigo, I'm just thinking, so we have like 3 X centers. Because yeah, it's actually, I mean, what he's saying kind of makes some sense because the angle bisector, like AI, meets the perpendicular bisector at the X center. So basically what Rodrigo is saying, like S is one of the X centers. And then P is another X center. And then this is going to be the last X center. Whoops. So S, T, and U are actually the 3 X centers. Let me clean up some stuff.
He told me to look like the triangle formed by the 3 X centers. We should look at the center of the homodity that takes one to another.
All right. So yeah, a lot of times those things sound scary, but I think
What?
Let's see. So oh no, these aren't the X centers. This is the center. So we could draw like the circumcircle of ABC, and those points will all lie on it, right? But the X centers, yeah, this is getting kind of messy. Yeah, I'm just gonna. It's hard to draw all 3 X centers at once. But he's saying to do a homotopy. It's gonna drive me nuts. Let's see what I can clear out of this diagram.
I don't know. It seems pretty difficult. And like, I think it's the most difficult problem, but because like here in Brazil, I think in the IMO too, we have like an order of the problems, like problem 1, 2, and 3. 1 is kind of easy. 2, it's a little bit more difficult. And 3 is harder. And like the same thing for 4, 5, and 6. And I think it's the most hard problem 5.
Oh, really?
Level 3, yeah.
Oh, wow.
Yeah.
But basically,
Yeah, thanks, Arabian math. I could enter there. Yeah.
Thanks for adding him.
Yeah.
So we still have 6 minutes left. So I could see what I could do in the 6 minutes. But basically, that W, V, and Z are the X centers. And it looks like Rodrigo is saying that it should be similar to triangle GMK. And I think we can actually prove that by an angle chase. So I actually don't think that part is too tricky. And the circumcenter of WVZ is R. No, R is the circumcenter of ABC. What is the, let me try.
What is the circumcenter of the triangle
Let's
ZWV?
looks like it's this point right here. And it looks like it might be collinear with the others. Let's call it, we're running out of letters here. I'll just call it F. I don't know if I've used, oh no, I already used F. A, B, C, D, E, F, G, H. R, S. I think I've used every letter of the alphabet. Okay. I'll just call it O prime, or I'll just delete this O and I'll call it O. So it looks collinear with the other. Let's see. Oh no. But is I R and O look collinear? So so O is the circumcenter of ZVW, and R is the circumcenter of ABC. And I don't think ABC is similar. No, ABC isn't similar to that triangle, but let's see. So if we zoom in a bit, it looks like R is the midpoint of IO. I wonder if that's true. Yes. So, oops.
Yeah, that's a great thing. Yeah.
So basically, the circumcenter of WVZ is like the midpoint of IO. I don't know.
And I understood. Yeah. Then we proved it. No, we have to prove that that's the midpoint. But if we prove that if the triangles MKG and VWZ are similar,
Mm-hmm.
we have that the midpoint is the circumcenter of the triangle.
I'm trying to think. Oh, because I is the orthocenter of WZV, right?
Yeah.
So, and H is the orthocenter of ABC. But it's not, ABC isn't similar to the other triangles, right?
No.
But do you still see a proof?
No, I'm just thinking like, I don't know, I just thought if we prove that, it's like, I don't know the word in English, but it's the same thing, I thought.
Okay. So I think it's probably really close to being solved. So if H is the orthocenter of ABC and I is the orthocenter of WVZ, let's see.
If you have to go, that's okay. Like,
I'll just, let me just think through this a little bit. So basically it's like we have two orthocenters, right? We have that, and we have, sorry, that's a circumcenter. And then O is a circumcenter. Yeah, it feels like if we can show R as the midpoint of IO, then maybe we could show N as the midpoint of IH. Is kind of, yeah, like what is the triangle in the middle? So if I take the midpoints, because the homosity is about point I, right? So if I like took the three midpoints, let's see. Yeah, I wonder if that would do anything.
I don't know, but it seems pretty difficult. I wouldn't do it on test. I would never have the idea of drawing the 3x centers like
that. Yeah. It
yeah.
looks a lot. This reminds me a lot of another IMO problem that used like a 9-point center. So maybe he had seen something like that before. I'm not 100% sure. But yeah, thanks for sharing the problem with us. So I think I'm going to stop here. But yeah, thank you both for participating and everyone else who came on earlier in the session. And for those of you watching on YouTube, again, this is our 8th one, and I don't think we're stopping anytime soon. So thanks for watching, and I will see you all later. So have a good day.
Yeah, you should record some problems from Brazil.